an attempt to show you guys a demo that I would normally do this time of year to explain kinematics or to make a dent on it. The device we're going to use this time is a motion detector. What this is it does echolocation. If you listen very carefully, I don't know if you'll be able to hear it in this video, but if you're in person, if you listen very carefully, you can hear it making clicking sounds. And so basically it's a little speaker and a microphone in here, and it sends waves out, and they reflect off the nearest surface and they come back. And then the software knows the speed of sound, can divide the time by 2 between sending out the pulse and listening for the echo. It's the same thing like whales and dolphins and sonar, and radar works that way, but radar works with light rather than sound. So a time honored technique. And so I'm going to put this in front of a track. I'm going to angle this camera down here a little bit so you can see the setup. So I've got a track here, and I'm going to put the motion detector at the top of the track. And you might not be able to see this very well, but it's inclined. This track is inclined so that this end is lower than this end. Maybe it's about a 20-degree, 15-degree incline. And so if I put a cart on here, right, this is designed to be almost friction-free. Obviously, you can't get rid of all the friction, but it's pretty frictionless. And it's getting pulled down by the not the entire force of gravity, right, because it's not in free fall, but some component of gravity is causing it to accelerate down this ramp, right? So we can see that it's getting faster and faster. So I've got Logger Pro up here on the other half of the screen, so I'm going to record some data from the motion detector. See what we get here. Okay. All right, so let me look at this graph with you here. So if we look at this first graph on the top here, this is position versus time. And then I think you've probably already seen a lecture, or you're about to see a lecture from me about the relationship when you look at a position versus time graph. Since velocity is the rate of change of position, that means it's the slopes on this graph. So in addition to reading this position versus time graph as a story, the cart was motionless right in front of the detector, and then it accelerated away from the detector, and then it was motionless at the bottom of the ramp, right? So that's a story that we can tell about that graph, just reading the graph. But now with our knowledge of physics and what velocity means, we can go a step further and we can look at these slopes, right? And so for the first 2 seconds, I have a flat line that has a slope of 0, which means the velocity is 0, right? And then from the 2-second mark to almost the 4-second mark here, I have positive slopes. So I had to click the photo booth so that I wouldn't be lagged out there. I don't really know what I'm doing here. So we have positive slopes here, and they are all positive, but they're changing, right? This is not a straight line. So I'm going forward because it's positive. That means away from the motion detector, technically. The instantaneous slope, if I were to draw a slope at that line, would be a small, shallow slope. And then it's getting steeper and steeper, which means I'm going faster and faster. And then I hit the bottom, right? And then I go back to a velocity equal to 0. So Logger Pro, of course, can calculate all those instantaneous slopes at every instant in time and plot them down here. And that's what it's doing, velocity versus time. And so let me expand this a little bit. It doesn't look like the velocity goes above 2. And of course, it doesn't really look like I have any negative velocities at all. So here's the story that we were just telling based on the slopes plotted for us by Logger Pro. So we have 0 slopes, values of 0 here, right? And that's because we don't have any velocity. And then the velocity is getting faster and faster. And so we have this increasing velocity with a straight line right here. And then at the end, when it crashes, of course, we come down here and we get the 0 again. So there's one final aspect of this story that I want to show you here, and that is we know what the definition of acceleration is, right? Acceleration is the change in velocity over the change in time. That would be the slopes on a velocity versus time graph. So in addition to reading off the velocity here, we can do the same trick we just did a second ago and talk about the slopes here and say that's the acceleration. So here I was holding the cart steady, and so the net force was 0 and the acceleration was 0. Then I released it. This is my hand letting go, right, for that little small instant in time there. Some complicated force. I haven't let go of it completely. I know that because the slope is changing, right, which means I have a changing acceleration, which means the forces involved are changing. Then I get a nice straight line again for the next second and a half or so, and that is when it's rolling freely down the track. And the only acceleration, it does have a constant free body diagram, which is giving it a constant acceleration, which turns out to be a constant slope, right? A positive slope, meaning it's a speeding up. And then it first comes into contact with whatever's at the bottom of the ramp, and it's brought to a stop quickly. Notice that here we can tell a little bit more details of the story. Over here, it appears to be an instantaneous thing, but it really is not, right? Nothing is actually happening instantaneously. It's brought to a stop quickly, and then the net forces are adding up to 0 again on the stationary object at the bottom. Now, LoggerPro can do the same trick like it did over here and graph all these instantaneous slopes and call it velocity versus time. I can change this one to acceleration versus time, and it will do the same thing, right? So it gets a little bit messier the further in you go, right? We're basically taking more and more derivatives in the language of calculus, but we're calculating instantaneous slopes, and now we're like 2 degrees of separation from the original data. And so it's not surprising it's a little bit noisy here. It's getting noisier and noisier. So you can see this is hovering around 0, right? Which is what we said the slope looks like here. And then this is the release interval of time. And then I have another instant interval of constant acceleration, which corresponds to this straight positive slope here, is giving me a constant positive value over here. And then it decelerates very quickly with experiencing a lot of forces. This is basically it crashing on the bottom. Notice that it's not an actual spike, right? It's in both cases, this is showing you the transitory forces that are getting it started as I'm releasing it with my hands and getting it stopped. And then at the end, once again, the net force goes to 0, right? So the story about the relationship between acceleration velocity and position or displacement is one of slopes, right? And so position versus time, look at slopes there, that tells you about velocity. Velocity versus time, look at those slopes, and it tells you about acceleration. And you could, of course, continue to play this game, but and mathematicians do, but physicists don't normally, right? Because at that point, we know where accelerations come from. They come from forces. And so these are the 3 kinematic variables that we are interested in. The object's displacement as it relates to its velocity, as it relates to its acceleration. And of course, what's on the x-axis all the time here is time, right? So those are our 4 variables that we're looking to relate. Okay, I'm going to stop here for the demo.